Hello, good afternoon, everyone. Thank you very much for joining us in this webinar entitled Social Innovation Talks. Please join me in welcoming back our speaker for today. He is an industrial design and solutions architect at Accelerating Makers. He is a huge fan of using traditional and digital methods to turn ideas into real products. He believes that ideas can come from anywhere, and digital fabrication technologies make it possible for anyone to design and create. Ladies and gentlemen, please welcome back Sir Gideon Catalan.
Thank you very much for the introduction, and thank you for having me here. Please let me know also if you can hear me properly. I think we're good. Yeah. Okay, good to see everyone, and thank you for the introduction. Glad that everyone is still here, and I hope that we do learn a lot. So I think based off the answers of the activity we had, a lot of people here have already some notion or preconception of what we'll be talking about. Many people here know about 3D printing. Either you've seen it in action or you've read about it. But we're going to discuss a lot more, because when it comes to digital fabrication or making things with digital tools, there are so many more ways that we can make things than just 3D printers. And throughout this entire presentation, some reminders. First, everything we talk about here are tools that humans use. So don't get overwhelmed with what the technology can do, and just remember that it's a tool for you to express yourself, your creativity. Next is, if you have any questions during the webinar, or if you want me to clarify or go over some things in better detail, just let me know. I have the chat box visible while I present. And so I'll try to answer your questions as they go. And if not, at the very end, we'll be having a Q&A portion, and I've chosen to allot more time so we can tackle these questions. This is also because usually when we're talking about these digital fabrication tools, there are a lot more questions. And on that note of the questions for the Q&A, as we go through the presentation, I want everyone to keep in mind a contextualizing mindset. Okay, we're going to talk about a lot of different technologies, different industries, different courses, but I want you to think of you, and I want you to think, I'm in this degree, I'm in this course, I'm in this industry. How could I use these? Okay, so it's all right for you to think about how you can take advantage of these technologies. And so the questions I'd like to see are ways that we can apply them to our own stuff. Okay, and then finally, around the 1 hour mark, which will be around 5-ish, depending on how fast I can keep up my pace, we'll be having a 10-minute break for everyone to refresh themselves from all the learnings. Okay. So without further ado, I will just start to share my presentation here. And if I cut out, or if the internet lags because the setup's kind of difficult right now, please let me know. Just raise your hand or put in the chat, and I can wind back a couple of minutes and then repeat myself. Okay. So I will now present my screen. All right. So let me know a thumbs up if the screen is presenting properly. I'll wait for the first thumbs up I see. Okay, I got 2. Thank you. All right. So again, welcome and thank you for being here today. Today we're going to be discussing Industry 4.0 as part of a series of talks here with HIFI. And today's topic will be about digital fabrication as well as FabLabs. And for our content, we separating it into 2 parts. Part 1, which will cover Industry 4.0 recap for those of you who missed the previous one. We'll also be discussing digital fabrication. What is digital fabrication, and why is it so much more than just 3D printers? It's a lot bigger. Then we'll have the refreshment break, which is around 10 minutes. And then for part 2, when we get back, we'll be discussing the maker movement, which some of us here may be familiar, we may even be part of it. FabLabs, a very cool idea. And then we'll finally have our Q&A portion, okay? And we'll be allotting extra time to our Q&A portion, especially for this kind of topic, because it really gets people's gears going when we talk about different tools of creativity. All right. So to begin, let's first recap our previous webinar. So in our previous webinar was talking about Industry 4.0. And what we did was we discussed first the history. So as a recap, Industry 4.0, they are industrial changes, which is why they have a series. And there were many changes. First one was mechanization and steam power, and then came mass production and assembly line, as well as electricity. Then Industry 3.0 was its discovery of automation as well as computers. And then Industry 4.0 is where we live in now, which is this new realm of cyber physical systems. We talked about how there's now digital places, digital spaces that we interact with. We talked about Internet of Things, which is this network of sensors and data gathering systems that allow us to see and gather data from everywhere. Okay. We also talked about networks in general. So this covered topics such as decentralization and how the internet in general has transformed how everything works. Whether you're talking about online shopping, whether you're talking about how you apply for a driver's license. The internet has changed a lot of processes, and Industry 4.0 is something that we're living in today. It's not a it's not a textbook historical event. It's something that we're living in if you look around and experience today, which is why it's very important that we understand that we're living in this new stage to open our eyes and be more aware of these changes. All right. Industry 4.0 is really, really big. And as I said before, as people who are living in it, who are experiencing its evolution, many of us are taking it for granted. For those of you who were born in the age of technology, you may have thought, for you, using this technology is second nature. It's natural to learn new programs, new video games, new computers, just like that. But for other people, it's new. And that's what living in a revolution is. It's a dynamic change, a revolution of the status quo. And to better explain, we'll just recap also some of the principles and drivers. So Industry 4.0, since I've mentioned it right now, it's very nebulous. It covers so many topics: health, politics, social welfare, economics. But in order for us to better see how Industry 4.0 works, we can first look at the principles. So these 4 principles guide Industry 4.0, and it kind of tells us and benchmarks that this is what Industry 4.0 is about. Okay, first is transparency. Transparency, because we have so much forms of data. We have collection of health data, we have environmental data, we have social data, like when we collect our sites we visit, how much time we spend on a computer, how often we go to a coffee shop because we log into their Wi-Fi. We also have data about how many hours we spend playing video games, how much money we spend on shopping, how many times we open our app. All of this data is reflecting this form of transparency, this ability to see and read and understand things. So compared to before, let's go with the example of the environment. Before, scientists had to make data based off of assumptions. They had to make projections off environmental readings. But when people started taking more readings, when there became an actual interest in recording the pollution index, when they started recording the temperature around the world, that data, that ability to see the effects of climate change, allows us to make better choices, meaning we know that climate change is happening because the data is there. And that data forms the basis of this transparency. Okay, so transparency is seeing data, seeing and reading and understanding things. Next is interconnectivity. So the internet, probably for me, one of the biggest inventions and probably one of the biggest forces and effects that we're having in Industry 4.0 has created this interconnected network, which is, okay, don't quote me on this, but it might be what the internet stands for. But this interconnected network of systems, these systems could be your cell phone. This system could be your computer. Even whatever device you're looking at this webinar now, we have created this interconnected network. And this has evolved to more than just computers. This has evolved to phones. This has evolved to your car can be connected to Wi-Fi. This evolved to your street lamps can be connected to Wi-Fi. The buses may have their own public Wi-Fi. You may have a local area network within your office that stores data. All of those are examples of interconnected networks. But you see, it grows and evolves even deeper when you imagine the world. Like, think about this now. You could have been sitting in your house in Germany, for example, and you could have joined our webinar. And because you can do that from around the world, you can have this level of interconnected systems, interconnected people from all over, thanks to this internet. And this interconnected systems, it does more than just, allow us to have webinars, allow us to see our friends, to play video games together. This interconnected network also allows us to send data. We could send information. You can open your phone right now and find out what's the weather in Cairo, Egypt. And that kind of data is possible thanks to interconnectivity. And it has so many implications, and it goes way deeper than just, our surface level understanding. But we'll leave it there. That's all right. The third principle of Industry 4.0 is decentralization. So the idea is, instead of data, instead of information or a system in general, being concentrated on a single place, a single physical space, like a computer server, for example, thanks to the internet, thanks to Industry 4.0, the information is now decentralized. You have this concept called the cloud, or being able to store data in multiple places around the world. And it forms this virtual network of information. And that idea of storing a virtual storage is what powers decentralization. We're no longer limited to central points of importance and information. We're no longer limited to a single DSL cable of a local ISP. With decentralization, our information can be everywhere. I may be presenting this webinar to you right now, but this data could have been shipped to Europe, bounced off a satellite somewhere across the globe, and then sent back to the Philippines. That's all about decentralization. It's no longer restricting things to a single central point. And thanks to interconnected networks, you have this decentralized system of components and units. Okay. The final principle of Industry 4.0, the fourth one, is assistance. So all the technology that we experience today has been developed or is in development as in effort to assist people's living. Your cell phone, your screen that you read, that is assisting you to understand information visually. These earphones that we wear, the speakers that play sound, they assist us to hear that information through audio. So all of these different technologies are such basic forms of assistance that we often don't realize. Your computer mouse assists you in inputting information to a computer through a physical touch. So on a basic level, those are some examples, but you can go higher. You have technology that assists you for learning. For example, virtual notebooks, ebooks, for example, even e-learning modules. You even have assistance in driving. If you have a car that may be advanced enough that makes a sound when you get near an object, those sensors that tell you that you're too close, they assist you. And all of these technologies have been developed because they assist people to do things easier, to make our lives easier. And when you think of it that way, a lot of all inventions that we have, this chair that you're sitting on, the screen that you're reading, everything is designed in some way to assist people, okay? So those four principles make up Industry 4.0. The transparency, interconnectivity, decentralization, as well as assistance. Those are what are the principles of Industry 4.0. Now, if those are the principles, we also want to look at what are the drivers. And so these are drivers, these are things that are happening that are pushing us towards Industry 4.0. And the funny part is these drivers aren't necessarily consciously being driven. There's not like some kind of group or conscious movement that is pushing people to go to the internet and make online services. No, these drivers can actually come about naturally through maybe assistance. First one example is consumer access. When you have the internet, right? Anyone can access it when they have an access to Wi-Fi or local connection. And if anyone in the world can access the internet, they have access to a whole range of information. And when you take that concept and make that normal, right? It's normal for me to look up what is the Fibonacci sequence. If I want to look up what does art in the Met Museum look like, it makes it normal for me to want to be able to access information. Makes me normal for me to want to know things. And this created this idea that thanks to the internet, thanks to these technologies, we deserve to know things. We deserve to know what our government taxes go to. We deserve to know what are the impacts of this particular business. We deserve to know what are the financial reports for our city or our nation, and how does the rising inflation prices affect us. All of these things become taken for granted and in a way standard because consumers desire this access. Now let's look at it from entertainment. As a consumer, I want to watch movies from Europe. And for us living in the internet, that's normal. Anyone can get that. And this idea that consumers want more and more access, we deserve, we expect this information, this level of information to come to us because the technology makes it so. And so I want you to take a moment and realize that this simple desire to do things, to know things, to access information, access video games, access movies, access art, information, whatever it is, all of those drive us towards Industry 4.0, that level of consumer access. Okay, next is digitalization of products and goods. So this one's kind of funny because we interact with a lot of digital systems. And if you are, no, it doesn't even matter what age you are. Everyone has interacted with something digital at some point in their lives. And more, we are interacting with more digital things, whether it's a digital video game, a digital board game, a digital investment plan. Digitalization of products and services comes naturally because we have so much technology that uses digital forms that it's so natural for us to say, okay, can I just do this digitally instead? Instead of having to carry a textbook, can I just have a PDF? Instead of having to go to a cinema, can't I just watch this at home? That desire to use technology to create digital versions actually pushes us to explore more and more what we can do with it. What are the limits of digitalization? Okay, so the simple act of converting these systems to a digital form drives Industry 4.0 further. It means that, okay, we want to look at what can also be digitalized. What more can we do? What more can we provide for consumers? And the last one is vertical and horizontal integration. So this one applies, probably it won't be, if you're not in an industry, if you're not a business owner, this may not be so visible. But horizontal and vertical integration simply means that a supply chain, which is like the manufacturer, the wholesaler, the distributor, and then the retailer, right? It's like a chain that the product follows. What the internet did is it shattered it into a linear chain, and it actually made it into a smooth process that has many different interactions. What I mean is, let's use an example. Online shopping. It used to be a very simple process. You go to a store and you buy something. But now, thanks to online shopping, we don't even have to go to the store physically. We can browse online. We can order a product, and then we could see where it is in real time. We know that it was delivered to the warehouse 2 hours ago. We know that it'll be delivered to my home in maybe 2 days. This ability to integrate different systems, well, that's one of the principles of Industry 4.0, drives us to integrate all these processes more. It's not anymore strictly a linear path, but now, because we have access to information, we can see all of it in play. And vertical and horizontal integration is also transforming how many industries function. Like groceries used to be very simple, but now we're looking at groceries that bring you from the farmer, meaning they can have their own page, and you can order as a consumer directly from them instead of having to go through a supermarket. You can look at products where they source organic food, and you can choose which products you want to get and then bring them to your house. So these changes in how the internet has affected our basic processes, like shopping, groceries, they've shown how much they can destroy is a harsh word. They have shown how much they can transform a vertical process into a, what's the word? A blown up decentralized process. It's not strictly a linear process anymore. And so all these things that are evolving, they're pushing us further and further into Industry 4.0. And when you think of it that way, it almost feels natural. And indeed, when you're living in an industry, you're living in Industry 4.0, many of these things feel natural. Of course, I'd want to access more things. Of course, I'd want more services to be digital. Of course, I want certain processes to be easier to do, thanks to technology. But when you see that it's driving this new change, this innovation, it kind of makes you think twice that, wow, we're really living in a transforming age. We're really in it. And that's my point. We are in it in Industry 4.0. So I hope that was a good recap for the previous webinar. And so now that we've covered Industry 4.0, one of the topics you want to cover is the technology itself. So we're looking at all these technologies, all this information, right? And we want to see what's come up. I talked a lot about new technologies, especially digital fabrication. And you'll see here that emerging technologies is hard to define because there's so many new ones. But some of the things that we'll cover, especially today and also in our next webinar, are the following. But today, specifically, we'll be covering first digital fabrication as well as FabLab in that topic. Okay, so in the next coming webinars, we'll be talking about smart cities as well as other technologies such as robotics, artificial intelligence, quantum computing for the future. But for now, we're going to focus on digital fabrication. And so when we talk about digital fabrication, the basic idea is this is making things with the help of digital technology. Okay, so digital fabrication to make things. And the first thing that I want to remind you, which is what I said in the start, was digital fabrication is a tool. It is a process. Fabrication is making something. But humans have to design. Humans have to decide what they're going to make. So throughout this presentation, we're going to talk about different industries which it applies to, different applications that you can make, different machines, what are the kind of actual technologies in there. But it's important to keep it human-centric, okay? Because I don't want us to think like, wow, with all this new technology, we don't need to do anything as human beings, or that we're being replaced. No, these technologies are new ways that humans can make things. And that is, for me, the very important preface, because it avoids a lot of very difficult arguments, I guess, when you talk about like replacing human workers or making the human useless or worthless. And it's not necessarily that accurate, okay? So going to our topic now on digital fabrication. So the idea is it combines 3D modeling, also known as computer-aided design or CAD, with additive or subtractive manufacturing. And that's the gist of digital fabrication. Now, the important thing to remember here is that CAD stands for computer-aided design, which means this is anything that you design or sketch your ideas in a computer. So this can mean a CAD software, for example, a basic one would be 3D modeling. If I wanted to make a character for a video game, I would use a 3D model. But it also applies to graphics. If I wanted to make a digital painting, I would use a illustration software. That technically is a form of design aided by a computer. If I wanted to make jewelry and I wanted to sculpt some very detailed earrings, for example, that process of making that model, making that design is still a form of design, but using a computer, okay? And one of the benefits of digital fabrication is the digital part. And this is important to preface because, I can't really see your screens at the moment, but give me a raise your hand or thumbs up or whatever if you know how to use Photoshop, Illustrator, Microsoft Paint. If you've ever had, for any reason, needed to use any of those software, let me know. Okay, I see a lot of thumbs up coming up. And I would tell you also that when you first learned how to use that software, did you learn it in a classroom? Or did you learn it making fan art? Did you learn it sketching some layout for your MySpace or whatever site you use? So one thing that's kind of cool is that digital also means accessible. Many of these technologies that we're talking about, computer-aided design, computer-aided sketching, anyone can access them if they know and are able to use a computer. And this really increases how accessible these technologies are. So let's compare that. If I wanted, for example, to make a painting, right, of me, or a beautiful oil painting of myself, you would need to learn how to oil paint. You need to have paint brushes, you need to have the paint itself, you need to have a canvas, you need to learn the skill it takes to draw that. And it's sort of like a barrier to enter, right? But what digital technology did was, by making all of this information, all of these processes available on a computer, which can do many things, not just that, they've made it more accessible. And this is a good way. I like using illustration software as an example, because from my experience, many people know how to use these software, not because it was their job, not because it was their course, but because they wanted to try it out, because they had a hobby, they had a passion for it. And because they knew how to use digital technology, it wasn't very hard to learn. You could have learned through a video, you could have learned through an online tutorial, like how to make a vector art on YouTube, for example. But the idea there is that digital technology, digital design is more accessible for more people. It has less cost in terms of barrier of entry. And as long as you're using a computer, you can actually use these technologies. And with that in mind, those of you who know how to use CAD, it could be 3D modeling, it could be 2D vector graphics, whatever it is, you can actually use these machines yourself. Yeah, okay. Now, when you talk about fabrication, we always imagine like a manufacturing plant, right? Some kind of long, complicated, dangerous, often, process of manufacturing something. But what digital fabrication does is it takes these technologies, right? This ability to manufacture things, and it combines the use of a computer to operate the hardware, the machinery. So instead of having to operate the dangerous equipment yourself, what happens is that the computer is the one that helps process that fabrication thing. So instead of you having to learn how to use a paintbrush, how to draw with a stylus, how to sketch with a 3D clay, for example, the software does that for you, right? The software does the color for you. The software does the thickness of the stroke. The software will tell you what kind of 3D shape you're doing. And that's what makes it digital. And the fabrication part is similar. Instead of knowing exactly, let's say, how fast the motor should spin, instead of turning a tool by hand or hitting it with force, the computer does that process for you. It knows how much force to put on the material. It knows how fast it should cut through the material. And that's what makes it more accessible, makes it easier. It combines traditional fabrication processes with digital processes, and boom, you have a digital fabrication process. So there. Now, before we talk about digital fabrication and the many different technologies that are in there, it's easier to set the tone first with applications, meaning where can I use this technology and how can I see it in action? So when you talk about applications, and we talk about digital fabrication, many people first think of engineering, right? They think of industrial applications, making cars, manufacturing planes, electronics. All of those are usually the first bit. But because of how versatile and how flexible digital fabrication is, they've actually started using it in a lot more subjects. But before we go to those, let's first look at engineering. So CAD was very synonymous with with engineering in many ways. Well, first and foremost, it allowed us to visualize complex shapes, complex processes, thanks to computer graphics. And so even complex machinery like this, complex mechanisms, or even the idea of a house, can all be simulated and generated using 3D files. But when you combine that 3D file, you can actually make things such as these. We've designed, using digital fabrication, for example, scale models. Even using basic shapes like plywood, we can make scale model bridge that actually is load bearing and actually uses the supports correctly. We've actually used this technology also to build electronics. So thanks to the ability to make very custom made parts that are very specifically shaped, you can make a design for a car that you designed yourself, right? You've seen custom PCBs. And if you've ever started in any electronics project, you'll know that it's very easy nowadays to have a PCB manufactured. The idea is that you use these digital technologies, right? And then you use a digital language. So for a PCB, let's say I design it in Eagle or KiCad, which is a software where you can design electronic circuits. And if you send it to someone who can manufacture it, they'll make you your exact idea in real life. And the idea here is that engineering, it's very synonymous with fabrication processes. But when you throw in digital, when you throw in digital design, when you throw in digital manufacturing, it makes it a lot easier. It's not something that's restricted to many years in an industry. Even new and novel designs is one of the places where digital fabrication prospers. DIY robotics. I'm sure we've seen like those crawling robots, or if ever you've seen they sometimes show them in science fairs. It's pretty cool. Like robots that can move on their own using a set of motors. These are actually often designed, custom made using a digital software. You 3D model the legs and you can work out the mechanics of how they move. Even things like clocks, or example in the bottom right, you have this example mechanism for a turning machine. And these are actually all made using CAD software and then cut with a laser cutter. So straying from the obvious, which is engineering applications, you can also look at architecture. So architecture is another frequent use for this, because when you talk about architecture, you're talking about a combination of structures, a combination of art with a form of construction. So architecture can involve building plans, from something as small as a bathroom all the way to an entire building. And we normally see, for example, scale models of architecture things. So you can have entire skyscrapers that are compressed into these small models. And what happens is they require a level of precision, right? Because to get us to scale a building down that small, to get everything perfectly right and lined up, you have to be very accurate. How small you cut the windows, how big the door is. And these kinds of ideas are made possible, like these kind of scale models, using these processes. So imagine a laser cutter that can cut to the precision of microns. Microns are super small. I think a hair is a couple of microns thin. You can actually cut these to that accuracy using a laser cutter. And it means that you can combine this technology, which is normally, let's say, for engineering, right? And combine them with topics such as art, architecture. You take concepts that are hard to imagine on a piece of paper. You know, if you've ever seen a blueprint, it's hard to read visually, but you can transform them into three-dimensional figures thanks to digital fabrication. If you've ever seen a plan for a building, it's kind of hard to read a blueprint. It'll tell you how big the room is, it'll tell you where the doors are, but you don't have that same feeling for how the space looks. So what they do is they make it in 3D. They use rendering software, such as CAD modeling, and they make you a 3D render of your house. They 3D render the room. And from there, you have a better understanding of the size, how big the space feels, the way it flows, important details that are only possible when you're looking at it in 3D. Then you can take it a step further. Instead of just staring at a digital 3D model, you can use a fabrication device that will read your 3D design and manufacture it in real life. So these are the ideas that go from, you know, a traditional idea all the way to a physical concept. And okay, so next one is manufacturing. When you say fabrication, very obvious. So traditional in manufacturing, processes have been going on for a long time, especially fabrication processes. But combining things such as digital technology has allowed us to open a new kind of thing, a new level of detail, a new level of production, a new level of customization and personalization. So the one I like to mention here is packaging. So when you look around you, right, you have so many different kinds of packaging. These are the boxes where you get your food, the wrapper of the chips you ate, the plastic bag. All of those are forms of packaging. And as many as there are packaging, there are as many products. You know, you have hundreds and thousands of different kinds of chips, different kinds of candy, different kinds of food. I won't even try to mention, but you know, there's just so many different kinds of things. And so what digital fabrication did is, rather than someone having to create each individual design on their own and then repeating that design by hand, digital technology allows us to create custom designs that are more fluid. And what do I mean by fluid? If you have a design, right, on Photoshop, for example, and you want to change the title, instead of, let's say, Gideon's cookies, you want to make it Gid's cookies. It's as simple as, you know, opening the text box and deleting the characters. But imagine if you had to paint that onto a tarpaulin by hand and you post it on a 4-foot wall. If I wanted to change my name, I would have to go through the process of buying a new tarpaulin, having it painted again, going through the entire process. And that would what? That's definitely harder than just pressing backspace a couple of times on a computer. Digital technology is more flexible and more fluid. especially when you look at digital design, because of how easy it is to manipulate digital data in a good way. um, it's easy to create your own designs. Like right now, we can all go onto Paint and then draw up some kind of ugly design for a new cereal. But we can, okay? You could, because the technology lets you do that. And what happened was this ability to create custom packaging, this flexibility and freedom to create digital examples of your design, this kind of opened up a new age for packaging. It opened up a new age for what people can do in manufacture. And then you combine it with new processes, like, for example, being able to print directly on cardboard, or being able to laser cut cardboard and materials to make thin shapes. You actually open up this new level of creativity that allows people to create interesting things, like these cookie baskets. So there. Another rising place that digital fabrication has come up is academics. And I want to preface this why, because we're living in Industry 4.0, right? And this technology is appearing everywhere. This technology is showing up not just in our homes, it's showing up in our businesses. If you were growing up and you wanted to work somewhere, you would have to learn how to use a computer, for example. And because schools have realized how important these technologies are, it has become part of the curriculum. There are more and more schools that are adopting digital courses. I think Benilde is actually one of the, from what I've gathered, is one of the leading multimedia institutions. So you see here that in the academic section, because people are learning about new things, it's only natural for them to want to integrate digital mediums. And what's cool is, okay, so when you're in school, right, the idea of shop class is kind of not really existent here in the Philippines, or not so often. But the idea was you learn something in school, and if you went to a factory which you wanted to work in, as an adult, you would have to learn how to use those machineries. You'd have to learn how to operate them there. But what happened was, when they took those dangerous machines that were operated by hand, and they put a computer in charge of it, they made a computer handle the dangerous processes, like pointing a laser beam or moving around the drill bit. What happened was they became, in some way, safer to use. How so? Instead of me having to hold a laser beam and cut a piece of wood, the computer will do that for me. I simply have to tell it what to do. And so it turned these technologies and created safer forms of fabrication. You can have a desktop laser cutter. You can have a 3D printer, right? So it opened up this new ability that instead of having to have these dangerous processes or these dangerous machines, these complex machineries, only be available for manufacturing, because there are digital versions of the machine that are safer to operate because they're digitally controlled, that are more reliable, that are safer because they're more compact. They realize that students can now actually use and learn how to operate these machines and have the skills needed when they go to the industry. So, for example, if you wanted to work in a, if you want to do automobile design, right? And you wanted to design engines, you wanted to design car body panels. Using a 3D printer, you could design it digitally in CAD. You can have it 3D printed and actually, in some way, manufacture your own custom car design. And that's possible because it's safer to use a 3D printer than to, for example, injection mold it yourself. It's easier to design it using CAD software. So digital technology made these processes, made these ability to learn and prototype these ideas safer. And so a lot of schools have now taken to adopting these digital fabrication technology in many ways and forms, which we'll discuss after the break. These schools have taken it upon themselves to introduce and properly learn and teach these digital mediums to students. And so, well, we already know, we're already familiar in Benilde that we have these digital technologies that are being used. But in other places, they actually have schools that are letting children as young as 8 or 10 years old laser cut and 3D print their own designs. They have classes where they're teaching grade schoolers, right, basic coding using blocks. They have toys that can help students assemble and create their own mechanisms. And all of this is because we're learning that using this technology, right, we could learn faster, we could learn safer and learn smarter. And so it's hard to see it clearly because well, we're not grade schoolers, so we can't appreciate it. But if you're a grade schooler and you learn all of these technologies when you're young, imagine the kind of experience and how digitally equipped you will be when you go into your work into the future. And so by learning these technologies now and by integrating them to schools, they actually transform the way that how fast people learn. And as a side effect, the technology itself becomes more usable. What do we mean? When younger people learn how to use this technology, it means that innovation can happen better because ideas now can happen from anywhere. Case in point, a student who's 20 years old who knows how to do basic electronics, basic soldering, CAD design, some 3D printing, they can actually manufacture their own thing. And indeed, it has happened. A Filipino inventor actually designed the world's very first vacuum forming machine because they had an idea. They knew basic electronics. They knew the idea of being able to build something and prototype and CAD design it. But because they were able to do that, they were able to invent and make their own new product. And if you look around, maybe for DOSD's projects in other schools, even in Benilde, I'm sure, there are so many new inventions and novel ideas that are coming about because people have access to that information, because people know how to make things. And when you see the importance of teaching this kind of information and the ability to create using these digital technologies, using digital mediums, it makes it a lot better. It makes it a lot faster, and it makes it a lot more accessible on who can innovate, right? Anyone can innovate. Okay. So all in all these things sort of build up this environment of learning, this idea that we want to fabricate things and make things, okay? Because you now have people who can use the technology because we know how to use digital media. We now have technology that's easy to use because they're digital fabrication. And thanks to programs such as this, which help share this information and ideas, and you have programs like FabLabs, makerspaces, SSFs, which give people access to the technology, that means that the innovation can come from anywhere. So I like the quote, Ratatouille. Not everyone will be a great cook, but a great cook can come from anywhere. So in the same way, not everyone will be a great innovator. Not everyone will be an inventor. But because the technology is more accessible to everyone, because anyone can learn it if they want it, great inventions, great ideas can come from anywhere. And that's why, for me, that academic area is very, very important when you talk about digital fabrication. Because when you give more people access to technology, when more people learn and elevate that body of knowledge, then it's only natural that more and more innovation will happen. And we've seen cases where, from the most surprising places, new ideas pop up. So digital fabrication and digital technologies are just a way of facilitating that and a way of making it more accessible to others. Okay. Now, when we talk about digital fabrication, it's very helpful now to look at what are the exact fabrication processes. So as a concept, we know about digital fabrication, but we want to see now what is actually going on. Okay, so let's first start with everyone's favorite, right? So this is called additive manufacturing. And many of us will know this by, ta-da, 3D printing. So 3D printing, and in this case, it has many titles. For example, fused deposition modeling. That's because they are all different forms of additive manufacturing. And when we talk about the other technologies here, you'll see that they may feel and look quite different than a 3D printer that you know, but conceptually they're the same. So in additive manufacturing, it's the process of making something by building it up. So as you see this wonderful animation here, you add layers and you make things. And that's the definition of additive manufacturing. This act of building can have many forms. It could be plastic, it could be paper, it can even be metal that you're putting together. But as long as you build the model up slowly, layer by layer, that is a form of additive manufacturing. And if you look at this list, I believe Nico, one of the names here, mentioned binder jetting as their topic. So I feel like it's a nice sneak peek, and also very advanced because it's part of the different technologies. All right. Now, when we look at the technologies themselves, the important thing to remember is that they're all additive. So it helps us to understand them. And the things you can make with them are kind of virtually anything. Not anything, okay, because there are some things that are impossible to make, but almost anything can be made using these processes. Why? The advantage of additive manufacturing is because you're building it up layer by layer. That means that complex shapes can be built slowly. Do I have an example here of something that's complex? Here. For example, this thing. Oh, no, the webcam is having a struggle. So you can do it. You can do it. Okay, there. So this is actually an engine housing from an engine block, right? And if you see all the holes in there, this is actually very complex to make. If I were to ask you to mold this out of clay, it would be quite difficult. If I were to ask you to cut this out of a piece of wood, like carve it up, I'm sure you would have an even harder time. But because additive manufacturing builds the layers, come on, you can do it. Because additive manufacturing builds it layer by layer, it actually is quite simple when you see it from that perspective. So it may look very complicated and, you know, with a lot of parts, but when you dissect it into each layer, it's like a big old pizza, you know, one slice, put the next slice, and then the next slice. So all of these shapes in this example look complex, right? You see complex patterns, complex geometry. But when you look at it from the perspective of building it layer by layer, it's easier to see how you can break down that complexity. And indeed, it's one of the strengths of additive manufacturing, the ability to make complex shapes. Okay. Now, this ability it's made more apparent when we contrast it with the opposing technology or the other kind of technology, which is subtractive. So for now, let's go again and discuss what additive is. So additive is when you have an existing material, right? And you attach or add material to it, making your product. Okay, so the first and most obvious one that many people are familiar with is 3D printing. Can I get a thumbs up or any emoji that you'd like to use for anyone who has seen a 3D printer in action? I want to point the camera to 3D printers so that all of you are affected. But the first one is called a 3D printer, which is usually called fused deposition modeling. And why do we call it that? Because in a 3D printer or FDM printer, it takes a spool of material. Usually this is plastic, right? It's like a string. And it will deposit it in a specific pattern or shape and fuse it together using the heat of the plastic. And when you fuse and deposit material in a specific shape and you model the final shape, you can get stuff like this. So example, our complex geometries such as this are made possible because it fuses that material together using the heat of the plastic by depositing it in a specific pattern. And the cool part about this is the machine deposits the pattern according to your design. So the machine itself is actually very flexible in what it can make. So believe it or not, one machine, looking at all of these to make sure it's applicable, can actually make all of these designs, which means whether you're using it for art, for architecture, engineering, even if you were using it to make a beer holder, all of those different shapes can actually be made using the same machine because it deposits it in a specific pattern. It's not limited to a specific shape or pattern. Okay, so next one is called SLA printing. So this may have other phrases or terms like resin printing, DLP. But the idea here is that instead of using a liquid plastic, we will be using a liquid resin instead. And this resin is cured or hardened using light. So what happens is there's a pool of liquid resin and a beam of light will harden the resin in specific points, generating the geometry. And so the benefit is because we're using a beam of light, which can be very, very precise, you can actually make very intricate shapes. So for example, in this case, the object is actually immersed in a vat of liquid, right? And a laser beam is shot and aimed at a specific point. And that point hardens the material and builds up that shape slowly. So, the laser will be like, and it goes up and makes a shape. So when we talk about SLA or any of these resin processes, they're usually a lot more accurate. They usually have finer detail because you can use a very concentrated beam of light to harden the resin. So the benefits are also, these are all usually used in more decorative, for example, jewelry. They're also used in cases where you need fine detail and complex shapes. You can contrast this because, for example, plastic, it has specific properties. It shrinks, it melts in heat, there are certain things. But in a resin, it has more flexible design parameters, meaning it's easier to create complex shapes like bones, architecture, small pieces of jewelry. They even have resin printers that can go as small as 30 microns. I think, no, that's definitely smaller than a human hair. There are very, very intricate things that you can make with SLA. Okay, so usually meant for jewelry or these kinds of applications. Now, next one is called selective laser sintering. Okay, so we'll break it down. So in selective laser sintering, it's selective because it chooses a specific part, which is the model. Laser, because it uses a high-powered laser. And then the keyword here is sintering. So sintering is the act of joining or sticking something together using heat or using a process. So this is actually very similar to SLA, right? In SLA, they use liquid resin. In SLS, or selective laser sintering, okay, they sometimes use powder of, let's say, metal or powder of polymers. And what it means is this powder of material is zapped by a laser that fuses it together. And so imagine the complex shapes that you can do with SLA, but combine it with the material properties of polymers. So this could be nylon, and you create shapes like these. These machines are usually more expensive because they usually need a very high-powered laser. But in turn, they produce output that are engineering grade, meaning very strong, very mechanically safe and sound to use. And there are a lot of things that you can do here. You could create intricate shapes. They're usually used in engineering applications. For example, where you need something to look like an injection molded part, but is actually made using additive manufacturing. And again, it's additive because you laser the powder and build that shape slowly layer by layer. Now, next one is called Polyjet. Okay, so to explain Polyjet, it's helpful to think of your desktop printer. So right in the desktop printer, the print head moves around and it shoots ink, right? Colored ink at specific points. What Polyjet does is it combines that technology, but instead of just shooting regular ink, it shoots resin ink that can actually cure and harden. And it does this layer by layer. And if you could take your DeskJet printer and make it print upwards, then you would kind of have the same thing. It builds it slowly using these small droplets of resin. That's why it's called jet. It jets it and sprays to make these patterns. And the similarity between DeskJet printing is that you even can use colors. You can even use colors. If you wanted to use, let's say, colored resin, you can actually make intricate shapes like these. So for those of us who are familiar with 3D printing, when I show them images like these, the usual idea is that, no, these were painted, or these were assembled, or they were post-processed in some way. But using a Polyjet printer, for example, allows you to have this level of control, and you can make multicolor prints like this. And if ever you were wondering what's like cutting edge technology, Polyjet is one of the cutting edge technologies in 3D printing. And it hasn't been fully widespread. It's very, very expensive. But seeing these things, the possibilities are actually really insane. They've been used in medical applications. So you see there, they can actually map out every individual vein and artery inside heart. They've done it for brain scans, where they can take the individual blood vessels inside the brain and print them in a 3D form. They've used these for surgeons. For example, if they have like a tumor in the kidney, rather than using a CT scan or a 2D X-ray to base their operation, they can 3D print a accurate life-like replica of the human body, and they can show those tiny details to help them plan this out. And it's really incredible the things they can do. They've used these for product design, where you could make bottles that look like real things. They've made this for art, where they've printed characters using Polyjet technology. It's really amazing. Now, the next two I'll discuss is called direct metal sintering. So this one's actually very similar to what we discussed about SLS, right? It uses the same word, sintering. But the difference here is it uses metal powder. And so a lot of the questions that are usually found is, can you 3D print metal? And the truth is, yes. You need a specific machine. They are actually quite expensive, but you can. So in this process, you can actually build up metal objects by lasering the metal particles together. And that's what direct metal sintering does. It lasers those metal particles and sinters them together into complex shapes. So some of the things that people have done with this is, because it's using additive technology, right? It can build these complex shapes. They've actually used it to develop lighter engine turbines. So imagine like this picture here in the top right. Imagine that complex, intricate network of parts. It has the same structural strength as if it were solid, but it's only 80% the weight. And those kinds of innovations are possible because of additive manufacturing. If I were to ask you to make that kind of structure using a drill, without destroying it, it would be impossible. If I asked you to cast that in a mold, you wouldn't be able to make that kind of geometry. There are things that are possible thanks to additive manufacturing, and these technologies make it doable, right? So again, it's similar to SLS, it uses a laser that lasers a powder, but this time the powder is usually metals. So that's direct metal sintering. Okay, next one is binder jetting. So this one was something Cernico posted on their name, I think. Okay, so to explain binder jetting, imagine you're at the beach, right? And you want to build a sandcastle. And there's this, just a dune full of dry sand. You can't build sandcastles out of dry sand. So what do? You pour water on it, right? You pour a little water, the sand gets a bit stickier, and then you can actually build up your sandcastle. So you get the same kind of idea in binder jetting. So what happens is, you have this bed of material, powder, sand, so to speak, and you actually jet a binder that makes the particles stick together. So once they've been jet together, you can actually build up that shape, and then you put it through an oven, which is what's happening in the top right, and it will actually mold it together as a single piece. So this is very common in terms of manufacturing processes. And so you get output that looks like this. And because you're using a powder and a binding material, you can actually make things out of both plastics, and you can make it out of metals. And because what they've done is they've actually used colored binder, you can actually make these colored shapes, such as the one in the middle. So interesting things you can do. Now, it's very funny sometimes to include 2D printers when we talk about 3D printing, but they are technically additive. So in UV printers, the difference between normal printers, okay, is that in UV printing, they print a special kind of ink that cures under UV light. And this causes it to harden with a better structure, meaning it's more resistant in terms of wear. And at the same time, because you're jetting and printing this ink that's very, very thin, you have all the benefits of 2D printing with the strength of making it a polymer while being super, super detailed. So some of the things that actually have been used, and if you've ever seen merchandise, you've probably seen something that's UV printed. You could print directly onto fabric, directly onto wood, directly onto plastic. UV printing is actually really cool, especially if you're in the graphics department. So we've always imagined, like when we make merchandise, your limitation is always, what stickers can I use? I want to make a sticker to put on a phone. But what if you could put your graphics and apply it directly onto your phone, directly onto a tumbler? And that's the kind of thing you could do with UV printing, because it prints a very powerful ink that binds itself to the material. You can get these kinds of graphics. And I think this is the one that I've been most impressed by when it comes to 2D, especially packaging, because you see ideas like in the bottom right. these eye-catching graphics that when you put them on objects, it makes you really realize that you could just put them anywhere. And there are a lot of cool applications, especially when it comes to merchandise, when it comes to giveaways, anything that's for personalization. Okay, so that's it for additive manufacturing. And again, it may seem very confusing, like there's so many different kinds. But the important thing to remember is that all of them are adding, okay? So you started with nothing, and then you're adding material layer by layer, okay? So that's what makes up additive manufacturing. Now, next one will be subtractive. But I think before we get too far into subtractive, let's take a quick 10-minute break. Okay, the next one we'll be covering is subtractive manufacturing. So this is actually pretty fun because when you compare it to additive, this one might be easier to understand. This may be for some people, if you've ever seen a CNC mill or a CNC router, that would be a form of subtractive. Now, let's go first in what is subtractive manufacturing. So subtractive manufacturing is kind of like sculpting, okay? And subtractive manufacturing covers many different machines, routers, milling machines, laser cutters. All of those are different kinds of subtractive manufacturing. And these kinds of applications, this intricate shapes, these wooden forms, you could be looking at brass, jewelry, even like metal assemblies, even furniture have been made using subtractive manufacturing. Okay, so really intricate shapes, even complex shapes, very heavy, hard shapes, can all be made using this process. Now, subtractive manufacturing is like this. You have an existing material, right, like a block, and you will actually cut away or remove material from that shape. And that's why we call it subtractive, because you subtract material away from your piece, leaving behind your product. So that workpiece can be many things. It can be metal, could be wood, many different things. But the same idea is there. So for example, if you're looking at a CNC mill, or in general, we call it CNC machining, it uses a drill and cuts away and shaves tiny pieces of material off very slowly. And that's how you make those shapes. If you're talking about a laser cutter, it will burn using a laser that material off to get rid of it, to subtract or remove. And one thing we can mention, like water jet cutters, it can even use something like water combined with some abrasive sand to actually cut through metals by putting it at a very high pressure. So all of these are forms of subtractive machines because they remove material to manufacture things. Now, when it comes to CNC machines, and this is something you'll hear often, CNC, this stands for computer numerical control. So CNC, whether you're looking at CNC machining, CNC milling, even 3D printing is a form of CNC, means computer numerical control. It means that a computer is moving and controlling the machine using a system of numbers. Okay. Now, onto the first one, CNC mills. So in CNC mills, it uses a drill bit, okay, a cutting bit to remove and cut materials out. So if you've ever used a drill and, cut a hole into a piece of wood, you're actually subtracting or removing wood to make that hole. And the same concept applies. So whether you're talking about a CNC mill, which moves in a 2D or XYZ coordinate, that's a form of removing. If you're talking about a CNC lathe, which usually rotates the material to make the shapes, also a form of subtractive. All of these have in common because they are using G-code. So G-code just stands for the language or the kind of commands that operate these machines. Remember, we called it CNC, computer numerical control. That's because the computer uses numbers to control the motion. So every shape, no matter how complex, can be interpreted as a series of vectors and points made up of locations, made up of numbers. And that's how the machine operates. So looking at G-code is kind of like looking into the mind of the machine. But yeah, it's definitely quite complex. Okay, so we saw CNC mills, right? Which uses a tool bit. Now we also have laser cutters. So I think laser cutters are quite popular because they are fast, they're pretty cool looking, but they also produce very, very nice and intricate output. And the idea here is the same. A laser cutter uses a high-powered beam of light, usually a laser, and it will burn the material, leaving behind the shape. So when you're cutting through wood, for example, it burns a line through the wood to cut out the shape. Alternatively, you have plasma cutters, which you can just think of as super beefed up laser cutters. Instead, they use high-powered plasma to cut through materials usually associated with metal. So plasma cutters usually for cutting sheet metal. One of the things you can also look at is water jet cutting. So this one's kind of funny because it actually uses high-powered water that's been pressurized to cut these materials. So even things like a lock, even things like fruits have been cut using a water jet. And it actually pumps the water at, I don't know if 60,000 bar, which is how much pressure is going through. So the same process still applies. The water hits the material and actually cuts and removes the metal as it goes. And another one in this technology, which also kind of counts, is called print and cut machines. So if you've ever had a sticker made, right? You've had it printed onto a sticker sheet, and sometimes you'll have a vinyl cutter, right? It cuts the material and cuts out the shape. So it's technically a subtractive machine because the blade is cutting the material and subtracting material as it goes. Okay, so the next one we'll discuss is 3D modeling. So throughout all of these conversations, throughout all these things, we've been talking about CAD, we've been talking about design software. And so we wanted to also mention, because it's a usual natural question, is what kind of software do I need to make the 3D models? And so when we talk about 3D modeling, there are many different approaches, many different forms. The one we can first mention is 3D scanning. So I don't know if anyone here has been lucky enough or fortunate enough to have been 3D scanned, but it's a very, very cool experience. Kind of like the idea of being digitized. But the idea is the machine uses light, right? Either it uses multiple light beams or flashing light to look at a pattern and make a 3D shape from it, making something like this. And so 3D scanning is one of the ways you can generate 3D models. But the other way, and this is probably the more common, is of course 3D modeling. So if anyone has ever done animation, if anyone's done CAD or engineering design, you'll know that it's a very different thing to illustrate in 3D. So the reason 3D modeling is so common and apparent is because if I were to ask you to draw for me a donut on a piece of paper, it would be kind of difficult. You'd have to do a series of rendering. You'd have to make shadowing and shading and certain amount of perspective distortion to make it interpretable, to make it able to be interpreted as a 3D shape. But with 3D modeling, because of digital technology, because the computer can render it for you, it's very easy to make 3D shapes. And that's why CAD is super important, because 3D, which is difficult to produce on a 2D surface, is made easier using these digital forms. So when we talk about 3D modeling throughout this, we're not specific to a certain software. I may use CAD or specific brands or software, but you can actually make 3D models out of many software. Some of them are free. So if you've ever looked into 3D modeling, there are free software and open source software that you can use. But the idea is still the same. As long as you can design your ideas in 3D, that's the kind of software that these technologies use. Now, just to put it all back into perspective and to help us interpret this network of 3D printing, right? We kind of separate into this matrix. So on the left side, sorry, I think it's right side. Okay, on the right side of your screen is subtractive, and on the left side is additive. Bottom is more 2D and top is more 3D. So the machines are usually fit to somewhere there. So for example, a 2D printer is more 2D additive, while a laser cutter is more 2D subtractive. A 3D printer, for example, is more 3D additive. Okay, so it's just a helpful way of interpreting and seeing these different machines. And there, just kind of like a map for us to interpret. Now, okay, so that was supposed to be the break a while ago. Okay, so now we've talked about all these technologies, all these digital fabrication forms. So one of the things I want to bring up are these three concepts: makerspaces, hackerspaces, and fab labs. Because we can talk about the technology all day long, but how does it affect us? How does it interpret in a way that we can use them? So digital fabrication has developed, or what's come about is these laboratories. And so these laboratories are spaces where people experiment and use these technologies. And the relevant ones that affect us, especially if we're in an institution like an academic institution, are makerspaces, hackerspaces, and fab labs. So they're all different forms of digital fabrication laboratories. And these different forms have different objectives. And in the case of the fab lab, may even be branded to some degree. So the first one is called a makerspace. So in a makerspace, the idea is quite simple. It's a space for people to make things. And it is intentionally general. It is intentionally vague because the idea in a makerspace is you don't want to limit any ideas. The goal is to facilitate the making, the ideation of anything, whether you're making a new musical instrument, whether you're making a new work of art, whether you're trying to devise a cure for balding, whatever it is, a cure for anything. A makerspace is designed to facilitate that act of making things, okay? And when we say space, this means a place, a location. This could be a laboratory. This could be a library. This could be someone's backyard. But it is a space dedicated to help people make ideas come true, okay? Now, a hackerspace is kind of similar in that it's also a space that is meant for new ideas, but it's called hacker because it has to do more with software. So if makerspace is more like hardware making things, hackerspaces are usually associated with programming, coding, new software. If you've had hackathons, or they have these events where they have to program things in like 1 day or 2 days, those are kind of like the same idea. They're spaces where people can come up with new ideas, but more on a software-oriented side. Now, those two ideas, hacker spaces and maker spaces, are general. They refer to spaces which promote and facilitate innovation and creating ideas. The next one I want to introduce, and is kind of the star, and I will give us time to talk about this, is the Fab Lab. So the Fab Lab was actually an idea and conceptualized by Neil Gershenfeld, who was an American professor in Massachusetts Institute of Technology. And Neil Gershenfeld said the concept was that he made it so that he wanted a place where they could make almost everything. And that's how the Fab Lab came about. So the idea was, it is a laboratory, a fabrication laboratory, or Fab Lab. And the idea was that it's a space where anyone can make almost anything. But what makes a Fab Lab specific is that a Fab Lab is actually sort of like a brand name. If the general term or the generic term of it was makerspace, Fab Lab is a specific type of makerspace. Because being part of a Fab Lab is being part of a global network. So from this map, there are actually Fab Labs all over the world. And if you look over here, we have quite a few in the Philippines already. And the objective of these Fab Labs is to learn and to promote innovation. How? By promoting a space where people collaborate together, where people use digital fabrication tools to promote their own ideas, to work together, to cross-pollinate ideas, and to collaborate together to make these ideas come true. And that's why Fab Labs have sprung up all over the world. Europe, we've got Barcelona, even one in Fab Lab Milan. And the interesting thing is, each of these Fab Labs can do different things. For example, the one in Belfast, it actually works with younger generations, meaning children, introducing digital technology to a younger age. In Barcelona, for example, this one works more with artists. So those who have like budding new inventions, new creations, innovative ideas that they want to try out. The Fab Lab helps make those ideas come true by providing them a space where they can test and make their ideas happen. In Milan, for example, this one works similar to an incubator. They look at startups, they look at businesses, new inventors, budding entrepreneurs who have ideas and products that they want to take to market. And they function as an incubator because they provide the tools for those startups to use. They provide the tools to make their ideas, their prototypes that they can send to investors, that they can pitch and present with, that they can make proof of concept models. And it helps turn a startup get on its feet and release actual products. So you see here, very different topics, very different target audiences, but all of them promote the same thing: collaboration, and innovation using digital technology. Even in the Philippines. It's just cool to see this global trend happening and then seeing that it's actually here in the Philippines and is happening right now. So one of the Fab Labs is actually in DigiHub, in Fab Lab Davao, which actually works to facilitate as an incubator. It seeks to incubate startups to make their projects able to go to market. And actually, one of the ones mentioned here, Fab Lab Bohol, is actually the first Fab Lab in the Philippines. And some of the Fab Labs here, their mandate is even to help MSMEs. They go to a location, they're established as a Fab Lab in that school, for example, and they look to assist MSMEs with innovation. So for example, if the MSME is selling local goods and they want to try using a laser cutter, rather than investing in their own digital fabrication machine, the Fab Lab allows the MSME to use their technology to come up with better packaging, better ideas. For example, PSHS has their own Fab Lab. And what they do is they allow students to work in the Fab Lab. So imagine you're what, 13, 14, 15, and you're operating a laser cutter. Imagine that on your resume. Imagine that they can interact with clients. They can interact with businesses. And that's what these Fab Labs do. They have this mandate to facilitate innovation, to provide spaces where people can innovate and collaborate together. And so Fab Labs, they've taken root in schools. They've taken root in government projects. They are government funded, and through the assistance of DTI, help promote innovation here in the Philippines. And so one of the questions that we always have when we talk about digital fabrication is, where do I go? So how do I access these technologies? And the answer is these Fab Labs, these maker spaces, who have the goal, have that mandate to actually use those technologies. All right. So I'm going to pause here, or technically stop here, and end my official presentation. And just to recap, we wanted to first discuss digital fabrication. I wanted to discuss why it's so important that it's digital, meaning it takes advantage of technology, digital technology, and that it's a form of fabrication, which is a way of making things. We also wanted to discuss in detail what are the kinds of technologies we can use. That additive manufacturing is more than just 3D printing. You have advanced, expensive, super cool looking machines, and then you have the 3D printers, the humble 3D printers. And I wanted to show just the depth of how much of this technology operates, how complex it can be, how advanced the applications can be. We also wanted to look at subtractive, because oftentimes when we think of additive manufacturing or digital fabrication, we think of 3D printers. But there's also a lot more. You've got CNC routers, CNC millers, even laser cutters, all different forms, but are also digital fabrication systems. And then, after we've discussed all of this technology, that for me is the perfect preface when you talk about Fab Labs and makerspaces. Because you have all this technology, right? We have all this innovation, we have all this readiness to create, but now we need that space. And that's what makerspaces, hackerspaces, and Fab Labs are. They're spaces that are designed to foster creativity. They foster collaboration between people. They foster innovation, making your ideas come to life. And because it is a space that fosters it, they use technology. They offer services for 3D printing, for digital fabrication, to help facilitate that innovation. And when you talk about Fab Labs specifically, you're talking about a specific project, a network of makers who seek to collaborate together and make these innovations happen. And finally, we wanted to localize it here in the Philippines. But Fab Labs are in action. There are Fab Labs here in the Philippines, in many of the major schools around the Philippines. And they work already with MSMEs. They have their own innovations that are out and about. And it's inspiring to see how these small laboratories are reaching out to their communities and making these innovations more accessible. So when I mentioned earlier that digital makes learning these technologies easier, right? Because it's digital, anyone can learn them. But these Fab Labs make the machines more accessible. You don't anymore need to be able to afford a 3D printer or a laser cutter, which could be many millions of pesos in cost. But using these spaces, using these programs, these Fab Labs, you can actually facilitate and start your own innovative process. So with that, I hope that we were kind of riled up in the possibilities of this technology, and I end my presentation here. So, okay, Pat, is that right?
We have one question right now in our chat box from Sir Nolly. So he said, how did you start your journey as an industrial designer?
Okay. Do we want the sugar-coated answer or the real one? I shifted to ID. So the reason was I always liked things with crafts. So arts and crafts and building with my hands. I like making things. It was always something that was fun. But there's not a lot of courses that say, oh, you can make stuff. Until I heard of ID, industrial designer, which was the idea was you design things, but you also have the aspect of industry, meaning for manufacturing. So it kind of gives you like the best of both worlds. You're not quite an engineer, but you are a designer. And since I couldn't get into engineering with my Jiwa, I went to ID. But yeah, there. So ID started, and it was where I started learning about design. But it wasn't complete until I found out about digital fabrication, because you can imagine, designing things is one thing, but making them usually costs money to pay someone to manufacture it or someone. And then you hear about a 3D printer where you can commission someone to print something for 200 pesos. And then suddenly your ideas, which were stuck in a computer or software, are suddenly now in your hands. And from there, kind of just like, wow. That's why I quite like the discussion on Fab Labs, because it's very close to my experience. It's a very nice idea, that collaboration and innovation concept. So yeah, it started from making things like arts and crafts, origami, basic things, and then I ended up seeing the beauty of making things, and then I found the beauty of teaching people how to make things and the technology that makes it. So if I would say that was the journey, that was how it goes for me.
Okay, we have two more questions that have been directly messaged to me. So the first is from Nats. He asked, what are the structural implications of using an additive type of printing compared to subtractive?
Good question. And okay, it's kind of a rabbit hole when you start discussing this, but generally, okay, the limitation of subtractive is you're working with an existing surface. So, okay, let's use a mug. That's easy. So if I wanted to use subtractive for this mug, a drill would go inside, right, and cut this. And then for me to cut this, right, you can't go from the top because you'd hit the handle. So your CNC machine actually has to go to the side and then cut it, okay? But a machine that can do that, that can turn the drill like sideways, they're quite expensive. So this is not something you can make on a cheap or desktop CNC mill, for example. But if you 3D print it and you imagine it layers, it's actually quite simple, because you make the base, you start printing the handle, then you make the rest of the cup, and then you just meet up with the handle here. So the idea is that undercuts, which are areas under the print, right? Those are undercuts. Undercuts are difficult to use on a standard CNC subtractive machine. Whereas on a 3D printing machine, undercuts are very possible. Interior shapes, for example, if this cup was upside down, right? I can't do the interior from the top. But a 3D printer, because it's printing it by layers, doesn't care, because the top doesn't exist. You're making it as it goes. So if there are structural implications, undercuts and overhangs are impossible with a standard basic CNC subtractive machine. Additive machines can do it much more easier, and they can generally do much more complex shapes. Conversely, if I were to say a weakness, is additive machines are very, very specific in material. They can only use thermoplastics, photo-curable resins, powders. Whereas subtractive, you can use a block of wood that you recycled. You can use a shell that you got from the sea. You can use a block of metal. Because you're subtracting from an existing material, you have a lot more flexibility, and the strength of the material is better because it's a block of material. So it's a very complicated thing, and there's a lot more into it, but there are a lot of differences. it probably would need its own webinar or two to just discuss that. But there, so just a little tidbit of the limitations of each kind.
You're right. It's a rabbit hole. We have one last question from Pao. So she asked, do you think 3D printing and printers can be accessible to all in the future, especially seeing these costs lots of money, like lots and lots of money?
Okay, so I would say that they're not that expensive anymore. Maybe 15 years ago, a 3D printer would have cost $1,000. Or no, let's put it in peso. Like, okay, not even 1,000. It would be like millions of pesos worth, a 3D printer. But now, you could buy a printer for as cheap as 8,000 pesos. I think there's someone who posted on the internet in a Facebook group that they found one in HMR for 5,000, a 3D printer. So I would say that the machines themselves have become more accessible for many reasons. But not just in terms of cost. Okay, so let's say that's still quite a lot. There are services like the Fab Lab, shared service facilities or SSFs, which are government-assisted projects, which means that taxpayers' money goes to making these establishments, and they provide these services to people to help them use the digital fabrication. So, you can actually commission people to print it. There's a huge community of Filipino makers. Facebook groups where people have printers and they do commissions for 3D printing. So I would say accessibility, because it's growing so much as a professional system, as a manufacturing, even as a hobby, it's very, very quickly going down. Yeah.
Thank you, sir. Well, I think that concludes our Q&A one last time. Again, thank you to everyone who sent in their questions. So going back, you can scan also the QR code shown right now, or visit our website at campsite.bio/Benilde to see our LinkedIn, YouTube, Instagram, Facebook, and Medium blog platforms. The link to our next event will also be shown there. So thank you again, Sir Gideon, Accelerating Makers, and the HIFI team for making this third Social Innovation Talk possible with Sir Gideon. And of course, we would like to thank our audience for joining us this afternoon. Once again, this has been Pat Cabansay, your host this afternoon. Thank you very much, and we hope to see you again in our future events.